All right, welcome everybody. So today we are going to look at symmetry within functions and some piecewise defined functions. And these topics will continue on in your next classes. If you plan to do trig, you're definitely going to see this symmetry. If you plan to do any of the calc series, you're going to see the symmetry and you're definitely going to see piecewise functions. Okay, so let's go ahead and start. Okay, so we have these three different situations here. We have symmetric with respect to the y, symmetric with respect to the x, and symmetric with respect to the origin. So let's go ahead and show you what that will mean, visually, just to make sure that we can all visualize that. So symmetric with respect to the y-axis, right? That might be something like a parabola. Okay, whatever you see on one side of the y-axis, remember this one's the y-axis, you're going to see the same exact thing on the other side of the y-axis. Okay, so there's an example of symmetric to the y. And we have, let's do symmetric to the x. So for symmetric to the x-axis, let me make sure that's clear, that's an x. You might have something like, let me think of an example besides parabola. It's always what comes to mind. How about this? Sorry, these are super shaky. There we go. Something like that, like an absolute value graph maybe, okay? Whatever you see on one side of the x-axis, you can imagine its mirror image on the other side of this x-axis, okay? And then symmetric to the origin is probably new to many of you. Okay. So that one's kind of the tougher, the tougher one of the two, or of the three, sorry, to explain. Let's see here. So symmetric to the origin would be maybe something like an x cubed, okay? And I'll try to explain it a few different ways, okay? Symmetric to the origin can be thought of as two reflections, and it doesn't matter the order. You could think of it as, okay, I'm going to reflect across the y-axis first, and let's say I take this piece right here, and that's what I'm going to reflect. So it comes over here like so. And then you do another reflection across the x-axis. And so the red piece that we just got will now come down here and will land on this other branch, okay? So that's one way to think of it, as a double reflection of half the graph, right? Another way to think of it is, so let me remove all these marks really quickly, you guys. Another way to think of it is that the graph looks the same right side up as it does upside down. So that's kind of nice. If you have a paper, right, you could just flip your paper upside down. So let me kind of show you what that looks like here. Okay. All right, so if you take the graph and you just flip it upside down, it is the exact same graph. You can see this matches, right? Okay. If you have that situation, and it goes through the origin, for example, okay, then that would be symmetric to the origin, okay? Another way to think about it is as a 180-degree rotation. So if you imagine just grabbing this branch right here, and you decide to take the whole thing and rotate it 180 degrees, then it will map onto this branch down here. Okay, so remember 180 degrees is half of a circle. So if you were to rotate it half of a circle, which you can kind of see right here, that's literally what I drew, as I drew about half of a circle, right? Okay, then it will end up mapping onto itself. So a bunch of different ways to think about it. Okay, it's good to be flexible and have many ways. All right, so to find out if you're symmetric to the y, you're going to substitute negative x in for x. To find out if you're symmetric to the x, you're going to substitute negative y for the y. So that's opposites, right? If I'm looking at the y-axis, make sure you do it to the x. If you're looking at the x-axis, make sure you do it to the y. And for the origin, you do it to both. Okay. So let's go in here and see what the heck that even means, right? Okay. Now, if there's a graph, well, let me show you the algebraic way, okay? So we're going to go in here and determine whether this is symmetric with respect to the x, the y, the origin, or none. That's what the directions say. Okay, so let's go ahead and do all of those. Let me set this up. Okay, so we're going to have symmetric. Let me make this a little bit smaller, you guys, so it doesn't take up the whole screen. So we're going to test symmetric y. Remember, that means negative x for x. We're going to test symmetric to the x-axis, which means negative y for y. And then we're going to test symmetric to origin. That means both. Negative x for x, negative y for y. Okay. Space these out a tiny bit more. All right, here we go. So let's start off by doing this first one where we're going to substitute in a negative x for all x's. All right. So we're going to take the original equation. We're going to put a negative x in for the x. So what that means is negative x times negative x times negative x. Remember, if you have an odd amount of negatives, it's going to stay negative, right? We have 3 of them, so it will stay negative. And then x times x times x is x to the 3rd. Now, what you want to ask yourself is, does it match the original? That's going to be the question you're going to ask every time, you guys. Does it match the original? Original. All right. It doesn't, right? We have a negative in front of the x cubed where the original does not. So no is the answer to that question. So our conclusion is that it is not symmetric to the y-axis. Okay. Let's try the one for symmetric to the x. So we're going to substitute a negative y in for the y on the original equation. Okay, and you can clearly see this does not match the original, right? Okay, so that's always our question. Does it match the original? Okay, the answer again is no. And so that's going to imply that this is not symmetric to x-axis, to the x-axis. Okay. Now we're going to substitute in both. We're going to put a negative y for the y, and we're going to put a negative x for the x. And we've already done the math to this right-hand side over here. So I'm just going to steal our result, okay? We ended up getting a negative x cubed, you guys, when all was said and done. Now I'm going to divide both sides by a negative 1. And when I divide both sides by a negative 1, that's going to get us y equals positive x cubed. So when we ask ourselves, does this match the original, right? Okay, our typical question we always ask. It actually does this time, right? Okay, that's exactly what the original equation up here looked like. So we finally got a yes. And so that will imply that this is symmetric to the origin. Okay. And we kind of knew that. So if you get a question like this on an exam and you're well aware of what the graph looks like, you're like, hey, that's one of our parent functions, right? I know what x cubed looks like. It looks like this. And you can just say to yourself, yeah, I already know that's symmetric to the origin. In fact, that's the example I just gave you guys, right? Then don't do all this work. Just be like, yep, yes, it's symmetric to the origin. Okay. And I'm perfectly fine with that because I want you guys to come out of this class with a really good understanding of all of the parent functions and what they look like, thinking visually becomes so important as you get higher and higher in mathematics. You want to be able to visualize things. Okay, so on that note, I mean, we could do this one visually. I claim that you guys, after, the last couple sections, know what x squared plus 5 looks like. So we know it's a parabola facing upwards, and it's been shifted up 5 spaces because of that plus 5 on the back end. So we have something like this. Wow, I cannot draw a parabola without shaking. That's going to have to do. Oddly enough, I kind of shook in a symmetric way almost. So yeah, so this does have symmetry. This is going to be symmetric to the y-axis, right? You can see right here for our y-axis, it looks the same on both sides. So if we're thinking visually, then our conclusion is symmetric to the y-axis, okay? All right, now if we wanted to do this algebraically, what would that look like? So let's go back really quickly. Oops, and I'm going to just steal so I don't have to type everything. I'm just going to steal this stuff, okay? Oh, is it going to let me? Yes, okay. I don't know what that's grabbing. One more time. Oh, I am going to have to type everything. All right, so let's see here. Probably good that we go over it and try to memorize it. So if we're looking for symmetry with respect to the y-axis, we're going to put in a negative x for all x's, right? We're looking for symmetric to x-axis. We're going to plug in a negative y for all y's. And then if we are looking for symmetric to the origin, and we're going to do both, right? Okay. Try not to run into my picture over here, but get as far to the right as I can. Okay. Some dividing lines. Here we go. Okay, so we're going to substitute in a negative x for all x's. So that's going to get us negative x times negative x. That's what it means to square it. Okay, so a negative times a negative is actually a positive, and an x times an x is an x squared. Okay, so we know that we're going to ask ourselves, is this symmetric to the, does it match the original? Sorry. And yes, it absolutely does, right? And so that implies symmetric to the y-axis. Now, you can't stop and be like, I found the one, right? You do have to keep going because you have plenty of figures that are like symmetric to multiple things, right? I mean, for example, if you looked at like a circle or an ellipse or something, right? Imagine I could draw a good ellipse. That would be symmetric to the y. That would be symmetric to the x. That would be symmetric to the origin, right? So you would have to go in and like legitimately check all of these because, it could be various ones. All right, so let's go ahead and do the negative y for y. So if we substitute a negative y for the y, that's not going to match the original. So does it match the original? No. So we aren't going to have symmetric to the x-axis, which we already knew, right? That up from our picture in the upper right-hand corner. Okay, so not symmetric. By the way, I'm going to circle this guy. Okay, now we'll try symmetric to the origin. So we're going to substitute a negative y for y. We're going to substitute a negative x for x. We're going to do both. So luckily for this one, you get to kind of steal some previous work, right? We already squared that over here, and we just got x squared. Does this match the original? Almost, but not quite, right? That negative y is ruining it. Okay, so no. So that implies not symmetric to, oops. Oh my. Okay, so let's see, how do I get rid of that line? There we go. All right, not symmetric to origin. Okay. So the algebra here really backs up what we got from the visual picture. Okay. You don't know this yet, but this is, no, you do know this. We did circles, you guys. This is technically visually, which is good for us to review these things. You know, we got a final one day to show you what's going on. This would be a circle centered at, remember, you have to change, there's a 0 here because there's nothing, you know, with the x, so 0, and then change the sign on this guy, right? So 0, -1 would be the center. So be right here, you guys. And remember, it's r squared over here. So if r squared equals 4, square root both sides to get r equals 2. So you would go, you know, 2 up, put a dot, 2 to the right, put a dot, 2 down, put a dot, and then 2 to the left and put a dot. And there's your circle, right? Okay. So I don't see symmetric to the x because this little bit isn't the same size as this little bit, right? So we don't have symmetry to the x, okay? And then, but it does look like it's going to be symmetric to the y. I do see this looks like the same amount as this looks over here. I mean, I didn't draw it perfectly, you know, but it is the same amount. Okay, and we won't get symmetric to the origin on this. So let's go in and do all these. See what we get. So from our picture, let's put our claim. From our picture, our claim is that we have symmetric to the y. So you're probably going, why do we have to do it this long way? Well, remember, not everything that you're going to get is going to be something that you have common knowledge of. I like to, on notes, give you things that you do have knowledge of so you can think about it in multiple ways. But the impetus for why we want to learn this is quite often this equation will be something that you do not recognize, right? And so you'll have to have this algebraic way of finding the symmetry if it's not something that you can graph, okay? All right, so symmetric to y. Symmetric to x. Negative y for y. I meant to hit space bar, not tab. Okay. Symmetric to origin. We got to do both. All right, you guys. Okay, so let's go ahead and substitute in a negative x for the x. So if we substitute negative x for the x, well, negative x squared, right? Negative x times another negative x, we've already done. That becomes a positive x squared. So the rest of it, we'll just bring along. Okay, now we have our, does this match the original? And it turns out that indeed it does, right? So it does match the original. So that implies symmetric to the y-axis. We already knew from our picture. Okay. All right, then let's go in here and see if they're symmetric to the x. So we're going to substitute a negative y for the y. And I think we can already see, right? Does that match the original? No, it's just off by that little negative in front of the y, huh? So this is going to be a no. Okay. And then we're going to try a negative for both. So let's put a negative in for both. Negative x for x and a negative y. So we know this becomes positive x squared. It's not really anything to do here, any math inside those parentheses, right? Okay. And so it looks like it is not going to match the original, huh? Okay, so put that down. Does it match the original? No. So not symmetric to the origin. It's great when the algebra backs up, you know, what we know to be true visually. Now these absolute values, I got to throw one in because they're kind of tricky. Okay. So, and by the way, another one that I claim that you should know visually, but I'm going to go with the algebra first, since we don't know the answer ahead of time. Let's go in here and see what happens. So we want to know, is it symmetric to the y? So negative x for x. Symmetric x. So negative y for y. And symmetric to origin. So let's try this. Okay, so we're going to put in a negative x for the x. Now, when you do this, I have a lot of students who will just put this down. They'll be like, oh, the absolute value brackets make it positive. And so they'll write that. But I want you guys to understand that this isn't necessarily positive when I write this. Think about it. What if x is a negative number? If x is -2, then what you are putting right here technically is a negative number, okay? So we can't write it that way. So what we do is we kind of use this little fact. So I'm going to put this at the top of the page. I'm going to put a note. The absolute value of negative x is the same as the absolute value of positive x. And whenever someone writes something down like this, try to think about it, right? So what I'm saying is, if I have the absolute value of -2, is that the same as the absolute value of +2, right? Are those equal? Is it okay to write that? Well, the left-hand side would become 2, right? And then the right-hand side would also become 2. So yes, it looks like indeed this is true, okay? All right, so that is what we're gonna use. We're gonna use that little fact to rewrite the absolute value of -x as the absolute value of +x. And it's important to remember the goal here, right? The goal is to try to see if this thing matches the original. That's always our goal. Okay, and so it looks like indeed it does. But we're getting a lot of symmetric to the y's today, huh? Okay. So let's go ahead and substitute in a negative y for the y. And I think we can tell that this is not going to match the original. So, oops. So does it match the original? No. So we have not symmetric to x-axis. Okay. Now we have to check if it's symmetric to both, right? So we're going to plug in a negative y for y. We're going to substitute in a negative x for x. And we know that the right-hand side, the absolute value of -x is the same as the absolute value of +x. And just looking right there, you can see that this does not match the original, right? All right. We have that negative y there, right? Okay. So this is a no. So this is not symmetric to. Now let's go in here and back this up with the visual. Okay, so let's get ourselves a little XY axis going. So an absolute value, if you recall, is a V, right? And because there's a -2 on the back end, this V will have been shifted down 2 spaces. Oops, I don't know if it's going to get any better with my second attempt, you guys. Let's see. Okay, that actually was a little better. Okay, so this does indeed look the same on both sides, right? So if I'm looking at the y-axis, right? So symmetry to the y-axis looks great. Okay, so totally supports our answer. All right, so hopefully you guys feel pretty good about symmetry with respect to the y, the x, and the origin. Now, we really, moving on into calculus and trig, we're really interested in the y-axis and the origin. Those are the ones that show up the most in future classes. And those actually have special names. Anytime that something is symmetric to the y, then it is called an even function. And anytime that something is symmetric with respect to the origin, it's called an odd function, okay? And you'll want to memorize these definitions. Now, let me talk about what this means and like why they give it these names, but also why it's important that you memorize the definitions, okay? So it turns out that the reason why they call something that's symmetric to the y-axis an even function is based off of, well, let's start with polynomials. If you take any polynomial, let's just do our basic one that you all know, right? Let's try x squared. So as long as the exponent is even, right? As long as all exponents are even, to be even more specific, okay? But we'll just do this simple case right now. Then you will get something that is symmetric to the y-axis always. Okay, so if we open up GeoGebra, so let me go in here, get GeoGebra opened. We could pick any sort of, polynomial and give it any kind of even exponent. So let's do x to the 6th minus 3x to the 4th, for example. The second I hit to the 4th, you'll notice that this picture became symmetric to the y-axis. And the 4 wasn't special, put in another even number, 8. There you go, you're still symmetric to the y. We could even tack on another, right? X to the 10th. There we go, we're back to being symmetric to the y. By the way, a constant, like just let's say I put a +3 or a +5 on the back end, that is actually an even exponent. Imagine there being an x after the 5, but it would be an x to the 0 power. So every constant is followed by an x to the 0 power. So some students get confused because they see the 5 and they go, oh, that's odd, but we're not talking about the coefficients. We're talking about the exponent on the variable x. So this one is x to the 6th, 6 is even. This one is x to the 8th, 8 is even. And this one is technically an x to the 0, 0 is even. So this will be symmetric to the y-axis, okay? Now you're probably saying, well, then why do I need this little test up here if all I've got to do is look at the exponents? Well, that doesn't hold true for other types of functions, right? For example, when you get into trig, cosine is an even function. It doesn't have an exponent. Well, I guess technically it does, but it's not a polynomial, right? Those things hold true for polynomials and rational functions too, and even absolute value x. Absolute value x, that's symmetric to the y because that's a v, right, you guys? But its exponent is 1. It's actually not an even exponent. So you do have to memorize this little definition up here because there will be functions that are not polynomials or not rational functions that you will have to use this definition to determine whether it is even or odd, okay? So, but I just wanted to make sure you understood that the name comes from polynomials and rational functions. All right, And then if it turns out similarly that if all of the exponents are odd on a polynomial or rational function, right? We already know this example, bring them back again, right? Then you're going to end up with something that is symmetric to the origin. You already know what x cubed looks like. We talked about it so much today. Okay. There's your symmetric to the origin. Okay. And so if we went in, let's check out GeoGebra again. And we went in and let's delete this guy out. We just picked some sort of polynomial with odd exponents. There you go, x to the fifth, that's already symmetric to the origin, minus 4x to the third. I made all my exponents odd, right? It might not be super easy to tell that this is odd. Maybe you can, maybe you can't. But remember, odd means it's going to look the same when I flip it, when I rotate it 180 degrees. So hopefully you know what that looks like and you've memorized it. I'm going to flip it upside down and it looks exactly the same right side up as upside down. So this is indeed symmetric to the origin. Okay. All right. So determine if the function is even, odd, or neither. Well, this is a polynomial. So we could do this two ways, right? One way would just be to go in there and put an x to the 0. Sorry, my pen's not working. Insert an x to the 0 after this constant. And so when we look at all of our exponents, they are all evens, right? So since they are all even, this would be an even function. And furthermore, what you need to know is that it would be symmetric to the y-axis then if we were to graph it. That would be you doing it, not by the definition. But let's get good at doing things by the definition, right? Okay, so let's go in and check that definition. Okay. So if we want to check if something is even, then that means that when I substitute in a negative x, I should get the original back. That's what it means to be even. So we're going to go ahead and substitute in a negative x for the x. So let's go ahead and do this. Go to the very top of the page and let's substitute a negative x in for all x's. Now, you know what the question is going to be, right? Does it match with the original? Okay. All right, so let's see here. If we took negative x 4 times, well, we said it, if it's odd, it stays negative. If it's even, it becomes positive. So this will be x to the 4th because you got x times x times x times x, right? If you did the same thing for the x squared, there's a minus sign, and then you've got to square the negative x, right? So these two together, a negative times a negative, would be a positive x squared, but it's going to be negative because of this negative out front, that minus sign, right? And then bring along your plus 2 that I didn't write down. All right. So if you look at it, that is the original, right? That matches the original. So, I mean, our claim is, yes, f of negative x is the same as f of x, right? When we plugged in a negative x, we got the same thing as up here at the top, right? Okay, so that implies that this is going to be an even function. Matched the original. Okay. And if you wanted to, which we want to check and see if this is I'm sorry, if it's odd, right? Which we already know it's not, but humor me. We got to get good at these definitions. The way that that works is you're still going to start by plugging in a negative x for the x. But instead of it matching the original, you want it to be the opposite of the original. Okay, so every single sign is exactly opposite. That's what we're looking for. All right, so we're going to go ahead and do the math, right? Okay. And we already did the math, right? They both start the same way. You just substitute a negative x in for x, right? And we did all the math to all this. Okay. And so since it isn't exactly the opposite of the original, I'm type this because my writing is kind of bad, you guys. Okay. It is not the exact opposite of the original. So it's not odd. Okay. So that's all you're doing. You're always plugging in a negative x for both of these guys. If when you plug in a negative x, it matches the original, it's even. If when you plug in a negative x, it's the exact opposite of the original, it's odd. You plug in a negative x and it's neither of those cases, then it would be neither even nor odd. Okay. Now this one gets some students. They will totally say, hey, this is an odd function, Mecklenburg. They'll come in here and they will look at these exponents and they'll be like, yep, odd, you know? And so they'll tell me that it's odd. But remember, we are inserting an x to the 0 behind all constants, right? So it's like, yeah, odd, uh-oh, right? So this should be a neither. It should be neither even nor odd. Okay, that's the conclusion. When we do the test, when we substitute a negative x in for x, all x's, that means it shouldn't match the original, nor is it going to be the opposite of the original. Okay, let's see what happens. Well, a negative times a negative times a negative. So 3 of them will stay negative. And x times x times x is x cubed. Here, we're going to take these two negatives, right? And we will make this a plus. I'll just put it in red. Sorry for the board glitching, you guys. Put the 3 back. There we go. So when we look at this, it is not exactly the opposite of the original. I have a negative in front of the x cubed, and this one doesn't. So maybe it's the opposite. Let's see. This one's the opposite sign of that one. Okay, so it's looking good so far for being opposites. But then the back ends are both +3s, huh? So it isn't exactly the opposite of the original. So this one's going to be a neither. Let's type that out. It doesn't match the original. So it's doesn't match the original. Nor is it the exact opposite of the original. All of the signs would have to change, not just some of them. Okay. All right, so this is a neither. Okay, let's try this one. So if we're, just so happens they're giving us all polynomials, you know, at this stage of the game, we don't have exposure to min functions. So I see why they're doing that. Okay, so I think you guys have a good guess. Those really are all odd, huh? So this is going to be an odd function, which implies it would be symmetric to the origin. Okay. Let's go in and check. So we're going to substitute a negative x for all x's, right? Okay. So we end up getting a negative times a negative times a negative. So it'll stay negative, x times x times x. And then we will take these two, you know, And we'll make them a plus. Okay. So looking at that, that is exactly the opposite of the original, right? The original was a positive x cubed. This is a negative x cubed. The original was a negative x. This one's a positive x. So since it's exactly the opposite of the original, I'm going to put in parentheses how we would say that in math. F of negative x equaled negative f of x, the opposite of f of x. Remember, a negative sign just means the opposite. Maybe I'll use brackets here, you guys. So it's not too many parentheses. Okay. All right. So since it's the exact opposite of the original, it is odd. Okay. So always plug in a negative x. All right. Always plug in a negative x and see if it matches the original or if it's the exact opposite of the original. So this is me summing up, right? Let's sum it up. Always start by substituting a negative x in for x. If it matches the original, if it is the opposite, okay, so that's going to be our little takeaway from this little bit. Okay. So it's the same direction. Is it even? Is it odd? But now we're doing it by picture. Okay. So we can see that this graph is symmetric to the y-axis. It looks the same on the left side as it does on the right side, right? So this is symmetric to the y. Okay. So it is an even function. If you're having a hard time memorizing that, just remember these two graphs in your mind, right? Just memorize these guys. You know x squared. You already memorized it, right? You know x cubed. You've already memorized it. Okay. And so notice what's true about even numbers. We have symmetric to the y. That's how I would remember come test day. Because it's not me memorizing anything new. It's me taking stuff I already know and using that to get these answers, okay? All right, let's try, oops, looks like we got a stray mark here. Okay, all right, let's try the next one. Okay, so this one is not even because it's not symmetric to the y. If I take this and I twist it, right, and I turn it upside down, you will notice it looks exactly the same as it does right side up. It looks exactly the same, right? So that means that 180-degree rotation, right? It looks the same. All right, so since it looks the same right side up as upside down, and that implies dot. All right. Remember, we said another way to think of that, like for some reason that's not working for you, is just to take one side. Say we take this side right here. I don't know if that's going to be beneficial on this one, so it's kind of hard, but to reflect it once. Yeah, I don't know if that's going to be beneficial, you guys. It's kind of hard to draw that. So I'm just going to leave that be, sorry. All right. So now we're into graphing our piecewise functions, okay? And so this one, it gives you the graph, so we don't have to worry about graphing it, okay? And we honestly don't even need the graph for this, but I'll use it to back up the answers that we get. So this is going to be a question. I think it's on your final, but it's also on, of course, this chapter test. So it says find f of -1. Now remember, whatever's inside the parentheses is always x because it's f of x, you guys, right? F of x. So this is an x value. So you want to figure out when x equals -1, which of these two pieces over here we're going to be using, okay? So to figure that out, you look here. You have to figure out which one of those inequalities -1 belongs to. So the top one is saying x is less than 0. Well, yeah, -1 is less than 0. So it looks like it's going to belong to the top one, right? Okay. So since it belongs to the top one, we're going to use x squared plus 1. Okay, so I'll put this over here. Since -1 is less than 0, we need to use the top equation. Let me make this a little smaller. There we go. So we're going to take -1 and we're going to substitute it into the x squared plus 1 equation. Okay, so if we substitute -1 in, -1 times -1 is +1, and 1 plus 1 is 2. So the answer to this should be 2. You're just reporting out what is the y value. Okay. And then you can go over here to the graph and you can double check that that is indeed right. So when we go to where x equals -1, which is right here, right? This is where x equals -1. Well, let's see what the y value is. If I go over to -1, I would go up 1, 2. So indeed, the y value there really is 2. So this looks very, very good. Okay, let's go and try f of 5. Okay, so we have to figure out, what, which one of those pieces we're going to be substituting the 5 into, right? Well, let's go over here to the right-hand side always. Is 5 less than 0? No. Is 5 greater than or equal to 0? Yes, 5 is definitely greater than 0. So because it matches or it fits or belongs to this bottom inequality, then we're going to be using this function x minus 1 this time. Okay, so since 5 is, and we'll have to split it, no, I'll start it now. Oops. Since 5 is greater than or equal to 0, bottom equation. Okay. So we'll use the bottom equation for this one. There we go. Okay, so that means we're going to be using x minus 1. So we are going to substitute 5 into that, right? 5 minus 1. 5 minus 1 is 4. So the answer should be 4. We go to our graph and we go to where x equals 5. 1, 2, 3, 4, 5. If we go to the y value, right, we go up 1, 2, 3, 4. So indeed, the y value is 4 for the x value of 5. All right, looking good so far. All right, so now the tricky one is going to be 0, because 0 is kind of like this dividing line, right? And so it matters these or equal to, right? So when we're trying to figure out which one of these inequalities 0 belongs to, this says x is less than 0. 0 is not less than 0. But 0 is greater than or equal to 0, right? So we're going to go ahead and use the bottom equation. Since 0 is greater than or equal to 0, we use the bottom. All right, so we're going to go ahead and use x minus 1 again, you guys. So if we use x minus 1 and we substitute 0 in, 0 take away 1 would just be -1. So that's going to be the answer for f of 0. And now you can see in our picture, x equals 0 right here on the y-axis. And so it's like, which one of these y values do I go to? Well, there's an open circle on the one on the top, and there's a closed circle for the one on the bottom. So I want to go down to the closed circle. That's an actual point right there, right? And so that would clearly be -1 if we went down 1. And -1 is the answer that we got. So you're basically finding the y values that correspond to the given x values, okay? So now we're going to do it without a picture, okay? So h of 1. So for that one, we have to figure out where we're going to substitute the 1 in, right? Okay. Well, let's go over here. Is 1 less than 2? 1 is less than 2, right? So I'm going to use the top equation, the x squared plus 3. So let's go ahead and substitute into the x squared plus 3 the value of 1. Okay, so 1 squared would just be 1, and 1 plus 3 is 4. All right, now let's go ahead and do 3. So we're going to have to figure out to which one of these inequalities 3 belongs to. Well, for the top one, 3 is not less than 2, but 3 is in between 2 and 4. So it looks like we're going to be using the middle equation, which is just the constant 7. So guess what? Your answer is 7. There's nothing to plug the 3 into. All right, now we're looking at h of 4. So if we figure out which one of those inequalities 4 belongs to, it's borderline, but it's going to belong to this middle one because it says less than or equal to 4. This one says greater than 4. 4 is not greater than 4, but 4 is less than or equal to 4. So we're going to be substituting it into, again, the middle, but there's nothing to substitute it into. So the answer is just 7. And the last one is going to be x equals 5. Okay, so h of 5. And so we can see that 5 is greater than 4. So we're going to go ahead and substitute it into the bottom one of 2 times x minus 1. So we're going to substitute a 5 in for the x. So let's do the math. 2 times 5 is 10, and 10 take away 1 is 9. So we end up with 9 for the answer. All right. I love these. These are, give me a bunch of these on the test, right? Okay. All right. So it doesn't really have directions, but I think what it's wanting us to do is to graph it because it gave us a piece of graph paper here. Okay. So when it's called a piecewise function, because you're actually taking just pieces of other graphs and kind of smushing them all together on one graph. So we really have 2 graphs here. We have y equals 1/2 x plus 1, and we have y equals -x minus 1. Now we're not going to take those graphs in their entirety. We're just going to take pieces of them. So for this first one, the y-intercept is always the last number, the b of the y equals mx plus b. So 0, 1 would be its y-intercept, and its slope is the m, so it would be 1/2. So I'm going to go to 0, 1. And then according to the slope, remember the top controls the rise, so the up and down, and the bottom controls the run, so the left or right. If it's positive, you go up. If it's positive, you go right. So we would go up 1, right 2, up 1, right 2. Or we could go down 1, left 2, down 1, left 2, whatever, okay? Now I'm not gonna graph the entire line, you guys, okay? We only want when x is less than 2. So I'm gonna find where x equals 2, which is right here, and I'm only gonna graph the line when I'm less than that number, so to the left of that number, okay? I'm not gonna graph to the right of that number. And then you have to figure out at the actual point where it ends, so at 2, if you're gonna make a solid dot or an open dot. Whenever it doesn't have an or equal to underneath the inequality, It'll always be an open dot. So I'm going to come in here and I'm going to open up this dot like so. Okay. All right, now we're going to graph this other piece, right? So our y-intercept is always the last number. So it'll be 0, -1. It'll be the b. So I'm going to put a dot on our graph. And then the slope is going to be the -1 that's in front. Now remember to always put it over 1 if it doesn't have if it's not a fraction already, right? And so we have to figure out if we're going to be going up or down or left or right. Since it's negative, we'll go down. Since it's positive, we'll go right. So we're going to go down 1, right 1, down 1, right 1. Okay, from that dot. Down 1, right 1, got down 1, right 1, down 1, right 1, down 1, right 1, etc. Okay. Now I'm only going to graph that green line when I'm greater than or equal to 2. So, 2 is right here, you guys. This is all 2. This is going to be our dividing line that's going to divide this guy up. I want to graph to the right of it. So I'm only going to graph this piece of it. And because it's an or equal to, I'm going to go ahead and make this solid. So I'm going to erase off all the excess, right? I'm going to erase that probably. That would be our graph for this particular function. Okay. Let's try another one. So this particular piecewise has 3 different graphs that we would have to graph. Nice, easy one. We'll take y equals -1, y equals x minus 1, y equals -2x plus 6. The y equals 1 is just a horizontal line. So we're going to just graph a nice, easy horizontal line. Now, that horizontal line is going to go through -1. So normally it would be like this. Let me make it red. Okay, normally it'd be like that. But we're not, oh, I should undo that. I have to draw it. Yes, sorry. We're not going to take the whole line, right? We're only going to take it when we're less than 0. So -1, I'm only going to take this part of it. Boy, shaky hands today. Okay, there we go. That's the less than 0 piece. And since it's less than 0 and not less than or equal to, I've got to open up that dot right there. All right, our next one is going to have a y-intercept of the last number. So 0, -1. And I should not do this in red because I already have a red line. So let me try green. So the y-intercept is 0, -1. So it'd be right here. And then the slope would be the 1 that's in front of the x, right? So from that dot, I'm going to go up 1 over 1, up 1 over 1, up 1 over 1, etc., right? Now I'm only going to be graphing this line. I mean, technically this is the whole line, right? But I'm only going to be graphing that line in between 0 and 2. So here's where x equals 2 at. Here's where x equals 0 at, right? And so I'm only going to be graphing this piece of the line. Oops. This piece of the line, you guys. The rest of it, I'm not going to graph. Okay. And I'm going to make it solid on both ends. So while the circle was open for a second, it's now been closed because this does have an or equal to on it. Okay. So it's going to end up being closed. All right, let's try our last one. We'll do blue for this. So we know that the y-intercept is the last number, 0, 6. I'm off my chart. I'll put them in there. And then we can see that the slope is going to be -2 that we'll have to put over 1. So instead of going up, we're going to go down to right 1, 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 etc. And I'm only going to be graphing this when I'm greater than 2. So here's where 2 is, right, all along this line right here. I'm going to go to the right of that. So I'm only going to graph this piece right here. This other stuff we will erase out. And that, since it's greater than 2 and not greater than or equal to 2, we're going to have to make this an open circle at 2. So you can see why it's called a piecewise graph or piecewise function, because I have 3 pieces here that I've stole from, other larger graphs, okay? All right. Okay, our last topic, I believe. Oh no, I forgot about increasing and decreasing, okay? So there's a function that shows up in calculus, and it's going to show up in our class, and it's called the greatest integer function. And it's technically defined, it looks like this, the symbols for it. So when you see those symbols, you know that you're looking at the greatest integer function. And so it stands for the greatest integer less than or equal to whatever value is inside. So I like to think of it as the round down function. So you're always going to, an integer is a whole number, you guys. So you're always going to round down to the nearest whole number, right? So round down to the nearest whole number. If it is a whole number, it stays the same. Okay, so that's how this works. So for example, 1.3, well, I'm going to round down to a 1. I'm going to skip this one. 5.6, normally you'd think round up. No, this always works as rounding down. And 3 is already a whole number, so it'll stay the same. Now, negatives can be tough. These are hard, right? You got to think about these. So let's say this is 0, and this is 1. Negative 0.2 would be like right here. So if I was going to round down, remember, rounding up would be going to the right. Rounding down would be going to the left. So the nearest one would be -1. So those are tricky, like something like -2.3. A lot of students will give me -2, but you actually made the number bigger. So to round it down, it'd be -3. So negatives, don't underestimate those. Take your time with them. Okay. All right. So they want us to t-chart this, this greatest integer function. So pick any values that you want to plug in. Okay. And so I'm going to just pick some for you guys. So why don't I pick like 0, 0.2, 0.7, 1, 1.2, 1.7, 2, and I think that'll be enough to kind of give us an idea of what this graph is going to look like, okay? All right, so if I substitute in, oops, sorry guys, left hand issues. Okay, so if I substitute 0 in, 0 minus 1 is just -1. And remember, all whole numbers stay where they are. So the answer will be -1. If we substitute in 0.2, oops, I forgot to do the -1, didn't I? -1. All right, 0.2 minus 1 will be -0.8. And remember, don't round it up. Make sure you round it down. So it'll go to -1. So at 0.2, which is right here, let's say that's 0.2, you guys. I'm going to go down here to -1. We substitute in 0.7. 0.7 take away 1 would be -0.3. Round it down, it'll go to -1 again. So at 0.7, we're going to go down again. Substitute in the 1. 1 take away 1. That's 0, right? Remember, all whole numbers stay where they are. So when you substitute in 1, you're at 0. So it turns out it's going to be like a horizontal line until I get here to 1. Then I'm going to hop up here to this dot we just made. Okay. And then for 1.2, if I do 1.2 take away 1, 1.2 take away 1 is 0.2. Oh my goodness, it's already so sloppy. Now other stuff's happening. And so I have to round down. Well, I'm not going to go up to 1. I'm going to go down to 0. So at 1.2, you guys, which is about right here, I'm going to be 0. For 1.7, take away 1. They would just be 0.7. Round it down to 0. So at 1.7, which is about right here, I'm going to stay. Turns out we're just going to get this flat line again until I get to the number 2. When I get to 2, look what happens. 2 take away 1 is just 1. And the greatest integer less than or equal to 1 is 1, right? Whole numbers stay the same. So when I plug in 2, I'm going to hop up here to 1. So what it's going to look like, let me just give you an idea. These greatest integer functions always look like little steps like this, little stairs, if you will. Okay. Okay. And so this is the reason why it's also called the step function. So the greatest integer function is also called the step function. Oops. That's because its graph makes these little steps like this. Okay. All right. So one of our last topics is really this idea of increasing, decreasing, and constant maxes and mins and stuff like that. Okay. So we all have to kind of agree to read the screen from left to right, or else none of this makes sense. Like if I have some curve, somebody could say, oh, well, it's decreasing because they're reading it from left to right. And they're like, yeah, that's a decreasing function. And then another person could just be like, well, no, it's an increasing function, right? So we're going to all agree that we're going to read everything like a book from left to right. So that's why when you see up here, this one would be an increasing function because I would be going up if I moved from left to right. This one would be a decreasing function because I would be going down from left to right. And this one would be considered constant because I neither increase nor decrease, I just stay the same. So that would be a constant function. Okay. All right, so let's go and look at some of these and describe whether they're increasing, decreasing, or constant. Okay. So there's going to be some pieces where we're increasing. I think we can see that this piece would be an increasing piece because we're going up. And I think that we can see that this piece would be an increasing piece since we're also going up. Okay, so we're going to describe those intervals using interval notation like the directions say. So remember, you're looking at x values when you're describing this. So there is an arrow at the end of this. So don't say from like -5 to, what is this, you guys, -2, because it actually keeps going, right? Okay. So we're just going to say from -infinity all the way to -2. Okay. And you're going to use parentheses on all corners. And the reason why you're going to use parentheses on all corners, like this corner right here, is because at that point, you can't really say it's increasing because it's kind of doing two things. You know, if you come at it from the left, it's increasing. But if you come at it from the right, it's staying constant. And so I can't 100% say, yes, at that point right there, the graph is increasing. So I'm not going to include it. How do we show not including something? Parentheses. How do we show including it? Square brackets. Okay. So just note that all corners will pretty much always be using parentheses on these things, you guys. All right, union. Let's go ahead and describe this other piece. So this is 1, this is 2. So it looks like it's going to be increasing from 2 all the way to, and again, there's an arrow at the end here. So we'll just assume 2 to infinity. All right, now let's go and find when this is decreasing. So it looks like the only interval on which it's decreasing would be that one right there. And so if we look at these two corners, those are in between 0 and 2 on the x-axis. So we're decreasing from 0 to 2. Whoa, a lot of extra dots showed up there. Okay, so our last thing to consider is when are we constant? Well, we're going to be constant when we have a horizontal line, right? And so the X values that is sandwiched in between would be -2 and 0 on the X axis. There we go. Okay, let's go over here and check out this one. So it turns out we're never increasing, right? So the interval on which it's increasing would be none. This graph is never going up. It's always, or it's looks like it's going down, right? Okay, so then if we're looking at when it's constant, I don't see this thing ever being constant. So this would also be a none for the constant, right? Never. There we go. Okay. And then for when is it decreasing? Well, it's always decreasing, right? So this would be from -infinity I should have done that in green, sorry. And some textbooks make you describe it like where the corners are taken out, and I can't remember what Connect Math does. So some textbooks, let me go in and check out our technical definition here. For decreasing, f of x1 is always greater than f of x2. Let me go back to the picture really fast. F of x1 is greater than f of x2. Yeah, I would just say this would be what we have, -infinity to infinity, right? Okay. All right. Now, we have, we're going to talk about something that's really important to us in calculus. We're going to talk about in business and lots of different fields. We're going to be talking about relative maximums and relative minimums on a graph. Okay, minima and maxima are the plural. Minimum and maximum are singular. So if there's multiple of them, you would say minima or maxima. Okay. So relative means I'm just going to include all maxes and all mins, and not necessarily the overall maximum and min. So let's say you have like a graph that's got like multiple humps in it. Okay. You know, if you were talking about what is the absolute maximum, there wouldn't be one because there's an arrow that goes up forever. But we're still interested in these little pieces right here. We would consider these to be relative maximums. We still want to talk about them. They're still important, right? And there's technically on this one, you know, no absolute minimum. You know, the arrow goes down forever. But I would be interested in these still. I would report those out as absolute minimums, okay? And it turns out, let's say you have a graph like this. Even so there is an absolute minimum this time. This is the absolute lowest. But not only is he an absolute min, but we also call him a relative min too. Okay. And there's another relative minimum. That would be a relative minimum too. So we'd have two relative minimums, and then we would have one relative maximum. And that's not an absolute max because there's clearly points that are higher. We've got an arrow going up forever. So there's points that are higher, but he is a relative maximum. And so, you know, you might think about like, why do I care about these then if they're not the highest? Well, you want to think locally, like maybe you're at the beach, and at the beach, everybody that lives there, there's this hike for this mountain, you know, and everybody loves to go on this hike. To the people at the beach locally, that mountain is significant to them, right? Okay. But when you think about that mountain's elevation, it's probably not very high because the beach would be 0 elevation, right? And so then that mountain can't be, you know, that high. That mountain would probably be lower than us here in the high desert, right? We're what, around 3,000? Okay, so we'd be like, that's not high, you know, but to them locally, it is significant, okay? And it might be significant for somebody in business because those tend to mark where you changed from increasing to decreasing, for example. So they'll want to know, hey, what happened in this month of March? You know, our sales were going up and then all of a sudden our sales went down. So it's not the highest spot for sales. There's other spots that are higher, but a business might want to look at that point and be like, hey, you know, what changed in that month of March? What made us go from increasing to decreasing? This relative maximum right here is very important, or even right here. What changed here in June, whatever that made us all of a sudden have our sales go up. We really want to look at, what happened during that month. Okay. All right. So we're going to go in here and we're going to identify not just the maxes and the mins, but the location of them too. So the verbiage is very important here because that could be confusing. When someone asks you what a max or a min is, you are always supposed to give out a y value. When they say the location of it, that means they want the x value. Okay. And just go back to that business example that I gave you, right? Let's say we have this function like so, and this is going to be your sales, in your dollars, sales in dollars. And this is going to be time, like the month, right? If somebody says, well, I want the relative maximum for the sales, right? Well, you would go here and you would look at this and you'd report out whatever that is. Let's say it's 500. And you'd be like, oh, well, there was a relative maximum of 500. Where was it located? Oh, it was located in the month of March. Okay. So the maximum wouldn't be March. You're not going to report out the X value. That's not the maximum. When you're looking at the maximum, you want to be looking at the Y axis. Okay. So I want you to take away from this. If I ever ask you for a max or a min, always give me the Y value. If I say, where is it located? That's when you're getting the X value. So we're going to go in here. Let's label some things right here at this vertex or corner. We have a relative minimum, a relative min. So let's talk about that. Okay. That is located at the X value of -2, right? And what is its Y value? Its Y value is -1. So it says the point blah. Okay, so a point is an X comma Y. So the point -2, -1 is the lowest point in a small interval surrounding X equals, so let's report out the X value, -2. So at X equals -2, the function has a relative minimum of, and I told you when I ask you for a relative minimum, give me only the Y value. Okay. Let's try it again for this point right here. That's interesting. This point would be a relative maximum. And that point would be 0 for the X value and 1 for the Y value. It is the highest point in a small interval surrounding X equals, well, 0 is the X value. So at X equals 0, the function has a relative maximum of 1. Okay, 1 is the Y value. Always report out the Y value. Okay, let's go in here and try these. So for relative minimums, I am seeing 2 relative minimums there and there. Those are going to be our 2 relative minimum values, okay? So let's get these X values. There's going to be an X value of -1, and this one looks like it's an X value of 4. So these are relative mins. So I'm going to put an X value of -1 and an X value of 4. Now let's get their Y values. At -1, it looks like the Y value is going to be -2. At 4, the Y value goes back to being 0 high. All right, now let's go ahead and get our relative maximum, because you can see right here, we're talking about maxes now. That would be our relative max, okay? Its X value is 2, its Y value is 3. So at X equals 2, the function has a relative maximum of 3. Now, something like this is tricky because, you might look at this point and say, that's a point of interest. That's got to be something, but it's nothing. Because if you take a small interval around it, it's neither the highest point, right? There's higher points. If I look over here, I found a point that's higher than it. There's lower points. This would be a point that's lower than it. And so it isn't the highest or the lowest in that interval. And so it's actually nothing. It's a shelf point. We call it any time where we have this situation like so. This would be a shelf point. Kind of imagine a man could stand there, right? So it would be a shelf. But it's neither a max nor a min when you have that situation, okay? So there is no absolute, I'm sorry, there is no relative max or min. No relative max nor min. Okay. All right. And another way to be able to tell is if your function's increasing and it's still increasing, then that would be nothing. When you think about relative maxes or mins, the graph changes directions there. Here I'm decreasing, decreasing, decreasing. After that, I'm increasing, increasing, increasing. And that's what created that min. For this red dot, I'm increasing, increasing, increasing. Now all of a sudden decreasing, decreasing, decreasing. I changed directions. So there has to be that direction change to create a relative max or a relative min. You can't go increase, 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 pause, increase, increase, increase. That's going to give you nothing, or decrease to decrease, that too. Okay. All right, you guys. So that concludes 2.7. Have a great day.